Excuse me, please.
So we can start now with the talk of Professor Portenko. Name of the talk is Brownian motion in Euclidean space with a membrane located on the given hyperplane. Please, Nikolai Ivanovich.
Okay. This presentation contains joint results obtained by Professor Bogdan Kopytko and myself. And before I start speaking on the topic, I would like to say that we dedicate this presentation to the memory of Grigory Lohanovich Kulinich, who died a few days ago. He was our colleague, our friend, and we dedicate this, our presentation, to his memory. At the end of my talk, I would like to formulate one of his results. That result, I was deeply impressed by that assertion that was proved by him about 50 years ago. So let me start, and I should, no, no, no new problem.
Maybe you have to.
Okay. Yes, yes. Okay, I understood. Okay. So the processes I'm going to deal with are determined not only by a hyperplane S, but also by a function Q of X that is given, that is defined on that hyperplane and takes its values from the interval -1, 1. This function plays the role of the permeability coefficient of a membrane located on S. In particular, if Q of X is equal to 1 identically, the membrane is not permeable for moving from the half space where X nu is not less than 0 into the half space where X nu is negative. In the case of Q of X being equal to -1, the membrane is not permeable for moving in the opposite direction. There is no membrane located on S if Q of X is equal to 0 identically. In the rest of cases, the membrane is partly permeable or partly reflecting. In all the known publications on the topic, the function Q of X was supposed to be continuous. Here are some examples of such publications. The starting, no. I am sorry. Is it visible?
Yes.
the starting point of our investigation was the following question. Suppose that we have some subset of S delta that is nowhere dense. And suppose that this coefficient of permeability is equal to the indicator of the set that is complement to delta. Then such a membrane must be reflecting at the points of S minus delta. And there must be no membrane at the points of delta. Okay, we call such a membrane porous. And the question was, is it possible to construct Brownian motion in RD with such a membrane located on S? And if it is so, how does its behavior depend on these and those properties of the set delta? I'm going to show how to construct the corresponding process for an arbitrary Borel measurable function Q of x, taking on its values from the interval -1, 1, and how to prove a certain limit theorem for the number of crossings through the membrane by a discrete approximation of the process constructed. I should say that the existence theorem is very simple, but as for the limit theorem, it needs much more subtle arguments for proving it. I would like to say that such a theorem is proved in the paper Portenko-Yefimenko in the case when Q of x is a continuous function. And we are going to prove it in the case of an arbitrary Borel measurable function Q of x. Okay? So we fix some unit vector nu. S is the hyperplane that orthogonal to that vector nu, and Q of x is given a given arbitrary Borel measurable function such that it takes its values from the interval -1, 1. Denote by GTXY transition probability density of Brownian motion in RD, and define the function G capital of the same arguments by setting GTXY is equal to this sum, where the inner integral here is a surface 1. I would like to draw your attention to the fact that S is a d-1 dimensional Euclidean space, and this surface integral can be understood as the Lebesgue integral in RD-1. Okay? The fact that that integral is well defined follows from the following inequalities. That integral can be presented as follows. It is estimated by, you see, this exponent. is it visible what I?
Yes, visible.
Okay, this exponent and this exponent gives this this expression, and this expression is this exponent with this exponent. This integral equals to this exponent because Kolmogorov-Chapman equation. Okay, and this integral does not depend on tau. The value of this integral does not depend on, does not depend on tau, and this integral can be calculated explicitly, and we have this estimation. So this integral is well defined. So and it is natural to put gtxy for y from S by setting it being equal to gtxy because integrand vanishes when y belongs to S. Okay, so excuse me, if q of x is, if we suppose that q of x is a continuous function, then the following properties was proved. For example, the proof of these statements can be found in my book. For example, this function satisfies the Kolmogorov-Chapman equation. Its values are non-negative. Its full mass is equal to 1, and it satisfies the inequality. So,
Mykola Ivanovich, and equation for G capital is not an equation, it's just expression. Is it correct?
Yes.
It's explicit expression for this transition density.
Explicit expression. That is because we consider hyperplane. If you consider a curved surface, then this transition probability density cannot be given in explicit formula. By explicit formula, you should solve some integral equation, and the solution determines the corresponding transition probability density. But because we have here hyperplane, then G is given by an explicit formula, and these properties can be easily established immediately from that formula. I would like to say that it is easily to make passing to the limit if we have some sequence of Qn that is pointwise convergent to some limit function Q, and this condition is satisfied, then the corresponding Gn goes to G. And if Gn satisfies this condition, then the G, the limit function G, is also satisfies that condition, and we have that function G gives us the transition probability density for any Borel measurable function Q of x whose values are in this interval -1, 1. And as a consequence, we have the existence of a continuous Markov process x of t in Rd, whose transition probability density is given by the function G, defined above for any Borel measurable function.
Nikolai Ivanovich, can I ask you a question?
Yes.
My question is the following. As far as I remember, Q and small is present in the expression for G capital only in the this surface integral. Am I right?
Yes. Yes.
So can it happen that for such conversions which you state in the theorem, it is enough to have only some conversions like every Schur with respect to surface measure?
Yes, yes. I would like to avoid the measurability, the back measurability, because some difficulties arises in that case. I would like to speak about Borel measurable function. Okay.
But my point is the following: if it is enough to have only convergence modulo of the surface measure, then one can expect that if such function Q coincides, then we will have the same Markov process. Yes.
Yes.
Yes. Yeah. This question was initiated by your initial problem, because if we consider dense set, which is almost all hyperplane modulo surface measures, and we will have the same process. Yeah. So maybe this dense set must be not very large, I think. Yeah.
Nowhere dense.
Yes, but it can be sufficiently large.
Yes. I will return. I will return at the end.
Okay, thank you
to this question. Okay.
Thank you.
The following property, the relation 1, is valid for in the case of continuous function Q of x. This is a consequence of the theorem. You see, this integral here is the normal derivative. You see this expression y nu over tau g tau z y. This is the derivative of g in direction nu with respect to this argument z, but this is equal to the same derivative with respect to y with the sign minus. Okay, so that derivative can be written here, and we have the derivative of single layer potential. And if the mass of single layer potential is continuous, then the theorem on the the theorem, well-known theorem on the jump of the normal derivative of a single layer potential says that these limits values are different if you approaches from point y from one side, from that side where zeta y is positive, zeta nu. This is mistake. In such a zeta approaches y in such a way that zeta nu is positive. Okay. This is the definition of GTXY plus, and the definition of GTXY minus is similar, but this time zeta nu is negative. Okay. In the case if Q is continuous, if Q is not continuous, is not supposed to be continuous, then we cannot expect that this relation is fulfilled at every point y from S. But something like this assertion is needed to prove the limit theorem that I claimed above. Okay, and in our situation, when Q is an arbitrary Borel measurable function, then the corresponding function G capital satisfies these two conditions. You see, now GTXY capital plus epsilon nu plus z, z is a point from S, nu is the normal to S. So this is non-tangent limit of this function. If epsilon goes to 0 plus, then non-tangent from that side where zeta nu is positive. And we have the following relation. This convergence is in the sense of L1 of in the sense of mean value convergence, in the sense of L1 in the S. Okay. Now let us consider that Markov process whose transition probability density is given by the function J capital, and let us consider random vectors x0, x1 over n, x2 over n, and so on. We say that a crossing through the hyperplane S takes place at the moment k over n if this product is strictly negative. For a fixed t, denote by eta nt the number of crossings through S by the consecutive values x0, x1 over n, x2 over n, and so on, x entire part of nt over n, the process. And the problem is to find out the limit distribution as n goes to infinity of the random variable eta nt, properly normalized. So one old Skorohod's result allows us to consider instead eta nt over the square root of n, the following sum. Here, command is Vn of x of k over n, where Vn of x is such a function. You see, this is mean value of crossings through S. On one step, mean value. You see, if we start from the point RD plus, from the point X that is in RD plus, then intersection occurs with the probability that the crossing will be at the time 1 over n with probability that is given by this integral, okay? And if we start from x in RD minus, then the probability that crossing occurs will be equal to this integral. Okay.
So I'm sorry. This Skorohod result relates to some class of functions G or what? You have some specific function. Did he consider your function G?
Skorohod's result concerned the sum of the normalized sum of independent random variables, but his proof, the proof of that result used only the following property. If you take difference between eta tn over square root of n and this sum, this is a martingale. Only this property was used by Skorohod for proving that lemma. Okay. And we have the same property because eta tn minus this sum is a martingale when t is changes.
Okay, thank you.
Okay, so this we can investigate this sum instead of this one. Okay, and now you see this sum became to be an integral sum if for the function square root of n Vn, and it is natural to expect that sum, that integral sum, is asymptotically the same, its distribution asymptotically the same as this integral. So our aim now is to investigate the limit distribution of this integral for fixed t as n goes to infinity. But this integral, its distribution according to Feynman-Katz formula, its characteristic function, say, is the solution to the following equation, to the following equation. This is a consequence of Feynman-Katz formula, okay? And the problem is now to pass to the limit in this equation.
Mykola Ivanovich, may I ask?
Yeah.
So you consider additive functional of a Markov process.
Yes.
And if you calculate characteristic of this functional and you prove that characteristics, sequence of characteristics converge uniformly, then you have
Limit theorem.
Yeah, limit theorem.
Yes. Because this integral behaves itself asymptotically as n goes to infinity, behaves as this sum and this sum as this sum. So we have, if I find out the limit of the function un, I find the limit distribution, okay?
Nikolai Ivanovich, as I remember, Feynman-Katz formula requires some conditions on the solution or for Markov process which we use in order to have such conclusion. So everything is okay here?
Everything is okay because this function for a fixed n, it is a bounded function.
Yes.
It is bounded by the constant square root of n, bounded, and it is measurable. So this there is no problem with this equation. Only we have to understand how to pass to the limit in this equation. And we need some information about this function, how this sequence of function behaves itself as n goes to infinity. Okay, this information contains in the following proposition that can be found in our paper with Svetlana Yefimenko. If Q of X is continuous, then the following relation is fulfilled for any measurable function phi of X, such that this supremum is finite, and this function has the limits, non-tangent limits, phi of y plus and phi of y minus. You see, this means that this function square root of n vn of y goes to delta function concentrated on the surface S, and this delta function is non-symmetric. You see, this formula utilized one limit value with this way, and another phi y plus with different way. Okay, and it is true for continuous function. And in our case, no, yes, and if you, I would like to remind in for if q of x is continuous, we have the following relations for gtx y plus minus. Okay, and now if we combine that information with this one, we can arrive at the following relation. In the case if q of x is continuous. Okay, in our case, q of x is not supposed to be continuous, and we have some more arguments to prove this lemma. This lemma utilized lemma 1, where that I would like to recall lemma 1. G has the same limit values, but in the sense of the convergence in L1 of S. Okay, and using lemma 1 and lemma 2, using lemma 1, we can prove lemma 2 that asserts that the same relation is true and for an arbitrary function q of x. Okay, and now it remains to speak about one more property of that integral equation that is needed to prove the main result of our presentation. And that property is as follows. You see, this, I would like to return to the function g. You see, as a function of tx, this is the single layer potential with this mass. If y is not in S, this function has no singularity at the point tau equals 0. If y nu is not equal to 0, this function has no singularity at the point tau equals 0. So this is the single layer potential, and it is continuous in t and x. Moreover, it satisfies the heat equation at the point tx if x is on the positive distance from S. So this function is not a bad function if t as a function of tx. As a function of y, it has some discontinuities at the points of S. But as a function of tx, it is a nice function. And so it is not surprise that this assertion is true. If we consider the following operator, that the function phi transforms in the function phi n, for n equals 1, 2, we integrate this function phi with this transition probability density and with this function square root of n vn of y. And it turns out that for fixed L and T, the family of function, this family is determined by n equals 1, 2, and so on, and by function, by an arbitrary measurable function such that satisfies this equality. So inequality. So we have the whole family of such a function, and we can assert that this family of functions is equicontinuous in Tx. Such this assertion was proved in our paper Portenko in 1987. Okay, and now we can pass to the limit in our equation, where is in this equation, because un is equicontinuous in Tx. So we can choose some subsequence which converges uniformly in X and locally uniformly in T and Xi. And then using the lemma 2, and this proposition, we arrive at the following equation. Mm-hmm. You see, here we have equation where the kernel of this operator is the transition probability density of Brownian motion. And one can expect that this equation is a characteristic function of some functional of Brownian motion in RD. And it is true. The following, let Wt be Brownian motion in RD, and we consider its projection on nu. This is a one-dimensional Brownian motion, and let eta t be its local time at origin. Eta t is the local time of one-dimensional Brownian motion, Wt product nu. Okay, and we denote by W tilde the orthogonal projection on S of the process Wt. So we can consider the following functional of this Brownian motion, because trajectories of eta are continuous and non-decreasing function. So this integral, it can be understood as the Lebesgue integral. And the theorem 3 asserts that the limit distribution in theorem 2 coincides with characteristic function of this functional. Okay, and now I would like to consider the following example. If Q of X, suppose that we have Borel measurable subset delta of S, and let Q of X be indicator of the complement to delta. Okay? Then the number of crossings through this hyperplane by the process with this permeability coefficient, the number of crossings has the limit distribution that coincides with the distribution of this functional of Brownian motion in RD. You see, this is the indicator of the process on S, W tilde. This is the projection of our Brownian motion on S. And eta is the local time of WT, inner product WT and nu. This is because you see we have here 1 minus Q of W tilde of tau square. If Q is indicator, square indicator is the same indicator. So 1 minus indicator of S minus delta is the same as is the same as indicator of delta. So we have that the limit distribution is the same as the time that the process W tilde spends in delta, but not real time. But that time is measured not in real time, but in local time of the process orthogonal to this one. Okay, this is the finish of my presentation, and I promised to formulate one result of Professor Kulinic, and I would like to formulate it. So I need to write here. Okay. So this result is the result of Grigory Logvinovich Kulinic. It was obtained about 50 years ago, maybe 60. And let us consider stochastic differential equation dx of t equals Rn of x of t dt plus dwt, where Rn of x equals n cosinus n x, n equals 1, 2, and so on. X is real numbers. Okay, and denote by Pn of x, the measure at the space of continuous function that corresponds to the solution of this equation starting from the point x. It means that the probability that x of 0 equals x equals 1. Okay, so it turns out that Pn of x converges as n goes to infinity to the measure Px, and this measure corresponds to the following, to the solution of the following stochastic differential equation. It is not equation, but is a Brownian motion multiplied by a constant k, where k is some, some j from 0 to infinity, j factorial to the power -2 to the power -1. You see, we have the drift. We have drift given by the function and cosinus nx. The drift is very often changes its sign, and its absolute value increases to infinity. Okay, and the limit diffusion, this is a diffusion, yes, and the limit diffusion is Brownian motion multiplied by this constant k. This sum is the value of some cylindrical function, but it doesn't matter here. And what is important, that this constant is less than 1.
Yeah, this is amazing.
Yes, this is impressive. You see, this drift lead us to diffusion without drift. Drift is equal to 0, the limit drift in limit equation, but diffusion is less than 1. And it is very interesting how to explain why less but not greater. I know very simple explanation to this fact, why it is increased and not, it is decreased, not increased. So this is very, very, very nice result obtained by Grigory Logovich Kulinich, and it was very sad news that he is no more. Thank you. That's all.
Thank you very much for very interesting talk. And maybe somebody have questions or comments, please.
It's very sad about Kulinich. My condolences.
Nikolai Ivanovich, can you show us slide number 20 again? The previous one.
Да.
Yes, this one. So this is actually the limiting distribution of your crossing number. Yeah?
Not distribution, but functional.
Yes, functional is the same distribution. My question is how heavily it depends on the set delta. What has influence? Only its Lebesgue measure, surface measure, or some other characteristics of the set are also included?
You see, its mathematical expectation is given by this integral from 0 to t d tau integral over s integral over delta g s x no s tau x y dy d sigma y and this factor. So if this integral is positive, so we have positive this set can be nowhere dense, but its Lebesgue measure can be positive.
Exactly.
So you have that if you have a porous membrane, the expectation of number of crossings through such a membrane limit distribution is this is the expectation. This is the distribution of a positive of a functional with positive values.
Yes, I understand this, but this is only expectation. Can it happen that for the sets delta which have the same this integral but a different shape, the distribution of those functional can be different? Because my point is that it can happen that you have porous membrane with one big hole through this membrane, or porous membrane with a lot of small holes, but the permittable responsibility will be the same.
The distribution, the characteristic function is given by this equation. You see, if Q is indicator of S minus delta, then we have here the integral over delta. Yes, and here d sigma y. Okay.
Yes.
In this distribution depends on delta.
Oh yes, yes. This is this my question. It will be very interesting to understand in which way, because it seems from the natural arguments that different that membrane of different shapes must have different different functionals like this one. So it will be interesting to understand what is a real difference and how the shape of the set delta has influence on the final distribution.
I may only say that the dependence on delta expressed in this equation.
Yeah, it is interesting. So
and maybe starting from some different point and for different delta, we can receive some the same distribution, but I don't think that it is possible for two different delta, essentially different, obtain here the same distribution.
Yes, yes.
For all x.
Yes, maybe so it is interesting how it depends on delta. Okay, thank you very much. Maybe some other questions or comments, please.
I would like to ask one question. Is it W functional in the sense of Dynkin?
Yes, yes, because you see, it's characteristic for this. Its characteristic is this integral, and this integral is equal square root over 2 pi integral from 0 to t e to the power x nu square over 2 tau, the tau over square root 2 p tau. And this is, of course, this is a W function.
And somewhere should be delta.
So?
Delta. There should be delta somewhere.
Yeah. This is over all S. This is estimation.
Yeah, this is estimation. Okay, so my another question is the following. You have a W functional as in this example, and you know that characteristic function of this W functional and of your limit coincide.
Yes.
There is a theorem in Dynkin book, for example, that if characteristics of W functionals converge uniformly, then you have convergence of W functionals in L2 sense.
Yes.
So,
Andrei, no, your question.
Yeah, and my question is, do you have convergence in L2 sense? Not only one-dimensional distribution.
Convergence of what?
Of your intersections, of your functionals. They are not W functionals, yes? They are not continuous.
Yeah, the number of crossings, this functional is applicable only for discrete approximation of our process. Because
yes, I understand. But it seems to me that Kulik has some works when he has observations and approximation, Markov approximation by sequences, and he got convergence of additive functionals as functions of T. And maybe you also have convergence not only of one-dimensional distributions, but a convergence of processes.
Maybe I didn't think about this question. Maybe.
Okay. Other questions, please?
Andrei, may I ask a very short question? Mykola Ivanovich, my question is the following. In that type of behavior which you considered here, so as I understand, you have the precise form of the transition probability, and therefore the analysis becomes much easier. But what about other kind of interactions? For instance, when you have some type of sticky reflecting boundary behavior or killing on the boundary. So in this case, the transition probability also can be done. So in some explicit way, where also analysis can be repeated similarly. Or this case is much easier because of only in this case you can write everything explicitly and therefore can work with that.
Vitaly, yes, this situation is very simple because I have explicit formula for transition probability density, but such theorems were proved in many papers of my students in the situation when S is not a hyperplane, but another, for example, sphere or something, or maybe a general surface in RD. And in that situation, we have no explicit formula, but we have some procedure how to, in that situation, transition probability density is expressed with the help of the solution to some integral equation involved this surface and transition probability density of Brownian motion, and using that information about corresponding transition probability density, we can prove such theorem for the number of crossings through that surface. And they much more complicated, but they are proved. Some versions of such theorems can be found.
So even in the case when S is just Borel measurable set, as you considered, in this case, you as on the slide when you consider the indicator and you have just purely reflecting behavior on the complement of the set S. Also, when you consider the same set for sticky reflecting behavior, also you will have a Markov process, right?
No. Delta is the subset of S. I spoke about S being not hyperplane, but more general surface, okay? And delta on S may be some Borel subset of S, because we can construct such membranes that this permeability coefficient is an indicator of a Borel, of an arbitrary Borel subset of that surface. Okay, so the number of crossings will be determined by this the limit distribution of number of crossings is determined by this formula. If the surface S is not hyperplane, then this limit distribution is much more complicated.
Okay, thank you.
Okay, thank you very much.
Yefimin, I'm sorry, Yefimenko defended his dissertation in 1988, and some results about limit distribution for number of crossings through the surface, through the membrane located on some more complicated surface than hyperplane. She proved, and there are some results in her dissertation.
Okay, thank you.
Okay, thank you very much. Other questions, please? If there are no other questions, then thank you, Nikolai Ivanovich, again for the interesting talk. And the next talk will be by Professor Xia Chen from University of Tennessee, Knoxville. And it will be devoted to hyperbolic Anderson model. Okay, see you in the next week. Bye.
Bye.
See you. Thank
Bye.
you for the
Thank
very
you.
interesting talk.
Bye.